Alright, so here we are with the 3.1 to 3.3 quiz review. Few problems to help ourselves review. In the first one here, we're determining the formula for an exponential function whose graph is shown. So if we take a look at what they give us, we are given that the initial point is 0, 3. So if we think of the formula that we tend to use, it's ab to the x, where a would have been 3 then, because it's the initial value. Then we need to talk about the rate of growth, but notice that from 0 to 2 is not one distance, and so a distance of 1, and so we need to actually use 2 and 6 as x and y in our equation in order to solve backwards and find b. So in that case, we're going to fill in our y of 6, our a of 3, and our b that we don't know, and then raised to our power of 2. So then we can start to solve. So we'll, for instance, take this multiplier and divide. So now we have 2 equal to b squared, and then we'll take the square root of both sides, and we get a b of the square root of 2, which is 1.4142. So that means that our equation is going to be always a y and an x still, but our a value of 3, and then our b value, I didn't leave enough space, of 1.4142. Actually, to be most specific, it might be nice if you just do square root of 2 to the x, but anyway. Alright, and then the next one we're going to do the same process, even though it's decreasing, but it does give you the initial point, that a value, so we're going to use that. We also have our x and our y. So if we plug it into the formula equation, we have 1 equals 2 times b to the 3. So we'll do the same thing as last time, divide by that value out front, so 0.5 is going to equal b to the third. And then take the third root this time, instead of the square root of 0.5. So the third root is under the math key of 0.5. So it looks like our b value is going to be 0.7937. And then our ending equation then is going to be y equals 2 for the original value, and then times 0.7937 to the x. Alright, so then we move on, and we're describing how to transform the graph of f into the graph of what originally would have been the parent function of e to the x or 2 to the x. Looks like both of these are e, so we won't be doing that one. Alright, so let's see. And then it says sketch the graph by hand. So, taking a look at what's happening, this first piece here of -3 and 2, those are the differences there. So there's a 2, and then there's a -3. So that 2 is actually going to end up, let's see, not stretch it, or it's compress it horizontally, because it's in Funky Town. Both of these are in Funky Town, so we're going to compress by a factor of 2, but anyway. Oh, and I should say that that's horizontally. And so by compressing it horizontally, that's actually stretching it vertically. And then for the next piece, the -3, that's going to shift it to the left 3. We'll do the other one, and then we'll graph them. So let's see. The two differences here is the number 3, which also compresses horizontally or stretches vertically. And then the -4, but this time it's not going to shift it left 3, it's going to shift it left 4. So not really a lot of difference there. So if we graph both of them, we've got our original function of e to the x, and e to the x goes through 0, 1, And then there's not really any whole numbers after that, but I guess there's 1, 3-ish, and then anyway, it goes up like that. And then the other one is the same for the original function. And so what's going to happen for the next one here in number 9 is that our exponent changes. So now we have 2x minus 3. And I guess I'll make it in green, why not? And so again, this number that used to be the intercept at 0, 1 is now going to be at 3 left, so oh wow, I was saying left and it's right. It's like doing the opposite of the opposite. Okay, anyway, it's right 3. Alright, so anyway, right 3. And then still up at your intersection of 1. And so it's going to be that same graph, only shifted. And then we also talked about how it compresses horizontally or stretches vertically. And so kind of instead of going up at this rate here that I've just shown, it actually is going to go up a little quicker. That doesn't look any quicker. Okay. That looks too quick. Okay. Alright, we'll go with that. Alright, and then the same thing happens over here, only now it's technically at a faster rate than the previous one, but of course now going through at 4-1 instead of 3-1. Alright. Then in our last problem on this page here, we're just going to find the exponential function that satisfies the given condition. So notice they're giving you the initial value. They're also giving you that it increases at a rate of 5.3% per day. And so remember, increasing would mean 1 plus the decimal value. So 0.53 is your percent. So that means that our equation is going to be initial value of 24, rate of 1.053, and then to the x. And then the second one is increasing as well, so 1 plus our rate of 0.167 and our population start. So our equation is, 67,000, and then 1 plus, oh, I don't really need to write 1 plus, I can just write 1 point. 0.167 to the x. So those ones are just filling in that formula from our formula sheet. Then the next one is finding the logistics function. So that one definitely you're going to want to reference your sheet, your formula sheet. And so your formula sheet is going to give you this logistics function here. And so we copy it over to our problem. Alright, so taking a look at the given pieces, your initial value is 12, so that's going to be x naught. Your limit to your growth is 30, and so it's going to be c, and it passes through an x and y of 20 and 2 and 20. So, in order to get our a value here, we're going to do an a of c, which is 30, over an x naught of 12, and then minus 1. So 30 divided by 12 minus 1 leaves us with 1.5 for our a value. So going back to our function, if we plug in each of the pieces we have, a y of 20 is going to equal a c of 30 over 1 plus 1.5 times b to the, oh, not x, but 2. Alright, and then we're going to have to go ahead and solve this because we need to get b in order to write the equation. So remember that means we're going to flip the fraction. So we now have 1 over 20 equal to 1 plus 1.5b squared, which means that we'd multiply by 30. And so now we know that 1.5 or 30 20ths is going to equal 1 plus 1.5b squared. And then we'll subtract 1 to get 0.5. And divide by our 1.5 that's being multiplied. And get 1/3. And 1/3 is going to equal your b squared, but then we will square root. And so the square root of 1/3 is going to be 0.5774. Alright, so that is our b value, which means that now we can write our entire equation, always have a y, so y equals, instead of a c, we're doing 30, and 1 plus our a value, which is 1.5, and then our b value of 0.5774, and then to the x. It's kind of sloppy on the end there, but it's an x. Alright, and then we do our next one here. Again, we want the same equation, so we have y equals c over 1 plus a b to the x, but remember that a is x naught over c minus 1, or close c over x naught. Okay. Alright, and so we'll start out by identifying what we have. So your initial height is 6, which means your x naught is 6, your c is 20, and your x and your y are 3 and 15. If we find our a first, a is going to equal c, which is 20 over 6. And so 20 over 6 is 3.3 repeating, so we're going to have 2 1/3. 2.3 repeating is our a value. So filling that in, we actually have 15 instead of y, 20 instead of c, and then 1 plus our a value of 2.3 repeating, and b to the x value of 3. Don't forget, when you're doing this value, you will want to actually have the entire value and not just an abbreviated decimal. So go back to the original value and create that. So to solve, again, we got to flip. So 1/15 is going to equal 1 plus 2.3 b to the 3rd over 20. But now we're going to multiply by 20. So 1.3 repeating is going to equal 1 plus 2.3 repeating times b to the 3rd. Subtract a 1 and get 0.3 repeating equal to 2.3 repeating times b cubed. And so this is where you want to use the whole number. So I'm using the whole 2.3 repeated. Whoops. And so we get b cubed equal to 0.3 repeated divided by 2.3 repeating. And so we're going to get, technically it's 1, how many are there? 3, 6, 7, 1/7. And then we'll cube root that. And so our b is 0.3780. And so ultimately our equation ends up being c, which is 20, over 1 plus a, which is 2.3 repeating, and our b value, which is 0.3780 to the x. Alright, moving on, we want to evaluate the logarithmic expression without using a calculator. So anytime we do that, you gotta rewrite your logs as exponents. So our base is 2, we'll raise that to the answer, and that equals what was inside. So 32 is actually 2 to the 5th. And so we match our x with our 5, and so x is 5 from the powers. The next one, it's 3 to the x is going to equal what is inside. 81 can be rewritten as 3 to the 4th. And 3 to the x, so x is 4. Alright, next one is a third root. So we've got a base 10 that you can't see, but it is there, even though, because they didn't write it. So 10 to the x is going to equal the third root of 10. 10 is a whole number, so those are always brought to the number of 1 as a power, but then this denominator is going to become 3. So we have 10 to the x equals 10 to the 1/3, and so x is 1/3. And then our last one changes it to natural log, so remember that means that we have an e as the base, so e to the x is going to equal the square root of e to the 7. And then just as before, that 2 becomes the denominator. So e to the x is going to equal e to the 7/2. So x is 7/2, or 3.5. Alright. This one, they just want you to rewrite it in exponential form, so really not different. Okay, so a 3 to the 5th equals x. That's it. Sorry, the next one is 2 to the y equals x. Super. Then we have a natural log, so base e, so e to the -2 is going to equal this fraction. And then the other one, it doesn't have a base, but it says log instead of natural log, and so we know it's a base of 10 brought to the answer, and then over equals a over b. So that one was just rewriting. Alright, the next ones, they want you to do your analyzing, so we're going to graph these equations just for a quick look at what's going on, and then we will find all of those pieces. Oh, apparently you've all been waiting for a response here. Okay, so I was graphing. I thought I had paused the video. So the idea is that it's going through at 1, but then it actually has this little tiny dip in it. So, and then an open value at 0, 0. Alright, and then it kind of continues up. So the next piece is 2, 1. And then 3, 3-ish. Kind of goes up that way. Alright, that's squiggly, but there it is. So our domain is going to be from an x of 0, but not including, because it's an open space there, to infinity. And then our range is going to go from, well, actually this minimum point. So we are going to want to find out what that minimum point is. So you can go to second calc and go to minimum, and then go to an x of, well, 0-ish, to something to the right. And so we're going to get a value of 0.3679 and negative 0.3679. Okay, that's funny. So our range is going to go from a y value of negative 0.3679 to infinity. Oops, forgot the y value. And then the continuity is that it's continuous on its domain. Clearly it stops at 0, but it's continuous on what we have. It's increasing. Oh, actually it starts with decreasing from 0 to this minimum point here. And then it's increasing from that minimum point to infinity. Never kind of comes back down. Then we have symmetry, and definitely not symmetric. It is bounded below because it has that minimum, so that's where that comes from. Its extrema is going to be a local minimum, and we've kind of already identified that, but it's 0.3679, negative 0.3679. There are no asymptotes. And our end behavior says the limit as x goes to, well, the easy one to the right is a y of infinity going all the way up. And then we have the limit as x goes to, whoops, I was trying to make a 0. 0 from the right. I guess it can't really come from the left, so anyway, 0 from the right is going to be 0. Alright. Next one's the same, so we're just going to do a graph here. And so if we look at our graph here, kind of squiggly line, but it's basically the same, just a little bit steeper because of this whole x squared. So our domain is going to go from 0 to infinity for our x's. Our range is going to go from this new minimum of negative 0.184 to infinity. Then we have continuous, and if it's decreasing or increasing, so this is continuous on its domain. And then it is decreasing as it was in the previous one from 0 to that minimum point of 0.607, and then it's increasing from that minimum point, so 0.607 to infinity. Then it asks about symmetry and boundedness, so it is not symmetric. And just as the previous, it's bounded below at the minimum. And then we have a local minimum of that coordinate, 0.607. And then there are no asymptotes as before. And then we pretty much have the same end behavior. So the limit as x goes to infinity of the function, so to the right is infinity. And the limit as x goes to 0 from the right of the function approaches 0 as well. So we have two more like this. So x squared natural log of the absolute value of x, so that's going to be different. We'll make a graph. Alright, so back again from our classic Zoom meeting. Alright, so here's our graph, and so we're going to identify all the super pieces of each of these. So the first one is going to be your domain, if I can remember all of them, and that's going to be all real numbers here. Oh wait, except 0. Not cool, because there's this empty space there, so watch out. We've also got our range, which is going to go from that minimum point, and both of them are a minimum at negative 0.184. And then they go to infinity. Sweet. Then the next piece wants you to do continuous and decreasing and increasing, so it is not continuous. Ooh, it's our first discontinuous. Discontinuous, and it's point discontinuity, because it's literally missing from that one point. Alright, then our increasing pieces are going to go from down at our lowest point to that 0, and then down at the next lowest point up to infinity. So we're going to increase on negative 0.607, the minimum, to 0, and then also from that next minimum point, so 0.607, to infinity. And then we have decreasing. Whoa, can't spell that. And the decreasing is going to go from negative infinity to that point that we have for our increasing, so negative 0.607. And then from that, let me think where I'm thinking. Oh, 0. Nope, from the, we're going decreasing. Ooh, from 0 to, oh, between here, 0 and 0.607. Sweet. Alright, and then our next piece is if it's symmetric or not. Oh my gosh, it is. So we'll type that over here, symmetric. On the y-axis, cool. Oh, my pen just turned off. Boo. And it's, where's the next piece? Bounded. Ooh, it's bounded below. That's cool. I just like when we don't have to put nothing. And then we have two local minimums. And I'm just going to draw arrows because lazy. Okay, so it's this point and then also this point. Technically, we kind of have a local maximum at those points where, because if we zoomed in, these kind of go and then they stop here. Like this point right here would sort of be a local maximum, but I'm not even going to go there. So that is something for calculus to investigate. And then bounded below, local, oh, no asymptotes, that's for sure. And then our limits of n behavior, so the limit as x goes to, now we get to do negative infinity this time, is infinity, and then the limit as x goes to the right is also infinity. Alright, so I'll finish number 42 and then our last page here in the 70s on the next video.